I decided to perform a set of upgrades to the 8080 computer system that I built last year. These are the 5 upgrades I decided to add. A drive activity indicator on the front panel. That required me to move the safety ground. I'm going to move the safety ground from where it is next to the reset button to the upper left-hand corner of the front panel. An I/O expansion bus to the main board. What I have on the main board is a serial console port and an ATA drive. I wanted to add a second serial port and a parallel port so that I can attach a modem and a printer. But in order to do that, I need an expansion bus because there's no room on the main board for these components. Which leads me to the need to build an I/O expansion card that plugs into the expansion bus, and that would give me an additional serial port and parallel port. But it will require me to write additional CBIOS drivers, reassemble and install an updated version of CP/M, and update some of my hardware-oriented utilities. To make the 8080 computer look more like a finished product, I want to add DB9 and DB25 connectors to the back panel for both serial ports and the parallel port. Right now, I just have a TTL cable exiting through a grommet on the back panel connected to a TTL to USB cable. Instead of that, I want to use classic RS-232 for the serial ports and the IBM pinout for the parallel port, which will connect to a dot matrix printer with a Centronics connector. The last upgrade is a switch to enable the Shadow ROM feature. I wrote some software utilities to do some hardware testing, and I discovered that the Shadow ROM feature can interfere with testing RAM 0 and other bits of hardware on the board. And occasionally, I need to make sure that the flash ROM always has control of the processor. So I needed a way to disable the Shadow ROM feature temporarily during testing and re-enable it later. The first thing I did was disassemble the 8080 computer. I took all the parts out of the case, removed the front and back panels, and started preparing the front panel for the installation of the drive activity light and relocation of the safety ground. I used a step drill to enlarge the hole used by the safety ground and then installed the drive activity light. The activity light is actually a push-button switch that I've converted to a display lamp. I've disabled the switch and replaced the original 12-volt LED with a 2.2-volt LED. A current limiting resistor will allow the new LED to operate with 5 volts. The switches I used on the front panel are modular. They can be completely disassembled, modified, and reassembled to do whatever you need them to do. This is what the case looks like with the front panel attached. You can see in the upper left-hand corner of the front panel where the safety ground is now attached. To simplify connecting the drive activity light to the ATA adapter, I decided to avoid the 12-volt rail and use 5 volts on the activity light. On the left is the circuit on the ATA adapter board that drives the activity LED. It's just one NPN transistor. That's all it is. The collector is connected to a 10K ohm resistor so that the activity signal can be connected to an external logic circuit. But it also has a 470 ohm resistor connected to 5 volts that acts as a current limiter for attaching an LED. To use the activity interface in the ATA adapter, I needed a connector, J9, over here, and a 2N3906 PNP transistor wired common emitter. When the ATA adapter transistor saturates, that causes a small current flow through the base emitter junction of the PNP transistor, which saturates its collector emitter junction and turns on the LED. The current limit for the LED is 100 ohms. Because as it turns out, this activity indicator is just a series of rapid pulses with less than 50% duty cycle. So in order to get the LED to an acceptable brightness and yet still remain below a maximum of 20 milliamperes, I used a 100 ohm resistor. If I'd have used the typical 330 ohm or 470 ohm resistor, the activity LED would have been too dim. On the I/O expansion bus, I decided to use a single row 20-pin female header connector for signal wiring and a single row 4-pin female header connector for power and ground. A single pin space separates the signal connector from the power connector. I've got a space right here. Using 4 pins for power and ground gives me a good low resistance path for powering all components on the expansion card. That's this up here. I assigned the address bus to the top end of the signal connector and then assigned the data bus the bottom end of the signal connector. And then I assigned control signals in the middle. A0 through A7 are the only bits that are used for I/O addressing on the 8080. D0 through D7 are the 8 bits of the data bus. There are only 3 signals needed for the control bus: I/O read, I/O write, and reset, labeled MR here for master reset. I don't need any clock signals, and I'm not using interrupts. I've left a pin available on the expansion bus should I need it in the future. The address bits on the I/O expansion card are used for chip select decode. I don't need to do anything to the main board to get the I/O expansion to work. This is what the I/O expansion bus header looks like on the main board. It's just a single row female header connector. Here are the 20 pins for all signal lines, and then here's the 4 pins for power and ground. On the I/O expansion card, I'm using 1 1/4 inch single row male headers. The long pins extend down from the expansion board and plug into the female header on the main board. The short pins are soldered to the I/O expansion side. I use these to provide clearance from the main board. This turned out to be a great interconnect solution. The parts are cheap and available, and I didn't need to do anything exotic to get them to fit on the board. But there is one compromise I had to make to use them. And that compromise is it can be a challenge to align the pins on the I/O expansion board with the holes on the main board. There isn't a lot of room in the case, and there's only about 1 inch of clearance between the boards. But after lifting the computer and putting it up on its side and using a head-mounted magnifier, I was able to easily connect the boards and verify that all the pins were aligned properly. It wasn't as hard as I thought it was going to be. Over here on the right, this is the Shadow ROM switch I installed on the main board. I wrote a set of flash ROM utilities to test the hardware on the main board and discovered that the Shadow ROM feature can interfere with some of the tests. So I decided to add a switch to allow disabling the Shadow ROM feature. After mounting the slide switch on the main board, it was a simple matter to unsolder the I/O write signal from pin 3 of U14.1 over here and solder it to pin 1 of the switch back up here. Then I soldered pin 3 of the switch to pin 2 of 14.1 down here. And after that, I ran a short piece of wire from pin 2 of the switch here in the middle to pin 3 of 14.1. It turned out to be a really simple modification to make. If the slide switch is in the up position, the Shadow ROM feature is enabled. If the slide position is in the down position, then the clock input on U14.1 is always high and the Shadow ROM feature is disabled. I like this upgrade because it turned out to be very useful for testing the I/O expansion board. As was shown in a previous slide, I removed the front and back panels from the case to make modifications. After marking out the position of the serial and parallel connectors on the back panel, I used a drill press to cut the mounting holes for the DB9 and DB25 connectors. Then I used a Dremel tool with a thin cutoff wheel to make the rectangular holes for the connectors. The metal used for the front and back panels is pretty soft and easy to work with power tools. It may be a little too easy. As you can see, I've got some overcuts here and there. These are hard to avoid when you're using a round cutoff wheel to make a rectangular hole. But I'll be installing the connectors over the holes, not behind the holes. So I think the connectors are going to cover up most of the overcuts. Here the I/O connectors have been mounted to the back panel, and I can just see where the cuts extend above the connectors when illuminated from behind, but with the case top on, the overcuts aren't visible. I left that grommet in there that was used for the old TTL cable. I left that in place. Now the back panel looks more like a finished product instead of a science project. The ATA adapter was originally stuck to the back panel with double-sided tape. It was always my intention to permanently mount it, but I wanted to find out exactly where the I/O connectors were going to end up. And as it turned out, I did need to move the ATA adapter down about an inch. I cut some holes for the adapter board and attached it using screws and brass standoffs. I completed all the physical modifications and now need to make hardware configuration decisions. Where are my new serial and parallel port going to reside within the I/O address map? Today, the console port is at address 0 through 7, down here. The ATA drive has two register sets at address 40 through 47, up here, and 80 through 87. I decided to put the serial port immediately after the console port at addresses 8 through F. And then the parallel port is after that at address 10 through 17. This is what the I/O address map looks like in bits. Address bits 0 through 2 are always allocated for I/O registers. Address 3 and 4 are the selector bits for I/O devices on the expansion board. The serial port is selected with 01, right here. The parallel port is selected with 10. A 00 on these bits selects nothing, as that's used on the main board. A 11 in these bits selects nothing, but could be used for a future I/O device on the expansion board. The top 3 bits of the I/O address must be always 0. These must all be zeros. A 1 in any of these bits selects nothing on the I/O expansion board. The 8250 chip uses all 3 register bits over here, but the parallel port only needs 2. I allocated 3 bits for register addresses anyway. Allocating a fixed block of address lines for I/O registers simplifies the design of the address decoders. That's why I did that. When designing control logic, I always look very closely at the timing diagrams provided in the CPU datasheet. Time spent here pays dividends in dramatically reduced effort and frustration. This is where most computer projects like mine go completely wrong. As I mentioned in a previous slide, besides the reset signal, which occurs only once in a run cycle, I only need I/O read and I/O write to control access to the I/O devices on the expansion board. I don't need clocks or interrupts or any other timing signals from the 8080 CPU. Reset is required because the serial port and the parallel port chips both need to be reset if the main board has been reset or power's been cycled. This is the only way to guarantee that my I/O chips have been initialized to a working state. Problems happen if you don't do that. Now here's a brief description of a simplified I/O write cycle. At the beginning of the cycle, address lines A through 7 will become active and stable, with the address of the device to be written to. A short time later, the data lines D0 through D7 will become active and stable, with the data value to be written to the device. The I/O write line will become active, which, based on the value of A0 through A7, will activate the device chip select and turn on the I/O expansion card bus driver down here. The bus driver direction line is connected to the I/O read signal, which is inactive during an I/O write, and the data bus driver is wired so that the default direction is always from CPU to expansion device. At the end of the I/O write signal, the write signal will become inactive. Tens of nanoseconds later, the data bus will become inactive. Now, this allows time for an I/O device to latch the data on the data bus before the address and data bus lines become inactive. Here's a brief description of a simplified I/O read cycle. It's slightly different from the I/O write cycle. At the beginning of the cycle, address lines A through 7 become active and stable with the address of the device to be read from. This is identical to the write cycle. A short time later, the I/O read line will become active, which based on the value of A0 through A7 will activate the device chip select and turn on the I/O expansion card data bus drivers. The bus driver direction line is connected to the I/O read signal, which reverses the default direction of the driver from CPU to device to device to CPU. So it just changes the direction of the driver. At the end of the I/O read cycle, the read signal will become inactive, which latches data from the device into the CPU. The address and data bus will become inactive shortly, very shortly after that, which inactivates device chip select and the expansion bus driver. This is an example chip decode design that will activate the correct signals on the I/O expansion board based on the address bus, I/O read, and I/O write signals. It requires 4 different 7400 series logic chips to implement, but it's been tested at full CPU speed and works as required. But I have nearly 100 GAL chips in inventory. So I decided instead of wiring in 4 7400 series chips, I'll use one 16V8. I'm using a Lattice GAL 16V8. Lattice stopped making these a few years ago, but Microchip still makes them and sells them through various parts houses. With a GAL chip, the decoder won't take up much space, and there'll be less wiring to do, which helps keep mistakes to a minimum. And during prototyping, it's far easier to reprogram a GAL than redesign and rewire a 7400 logic decoder. But the disadvantage is that you need to understand some simple logic equations, you need some software to build the GAL fuse map, and you need a PAL-GAL programmer to set the fuse map. The good news is that Microchip provides a logic compiler for programmable logic chips for free, and a good PAL-GAL programmer can be purchased on Amazon for about $80. That makes working with programmable logic cost-effective for the hobbyist. To use a GAL, you first write logic equations that express your desired output based on a combination of inputs. Notice on the left-hand side over here are my 3 outputs: serial select, parallel select, and I/O buffer enable. On the right hand are all the equations I used to enable these outputs. The syntax for these equations is very simple. An exclamation point is a NOT operation, a hash mark is an OR operation, an ampersand is an AND operation, and the $ is an exclusive OR. All I did was just take the 7400 logic schematic I showed you earlier and render it into the equations shown here. I didn't spend any time trying to optimize these or make use of positive logic or negative logic, etc., etc. I didn't do anything other than translate the schematic into a set of equations. Since this is a relatively simple design, I'll let the Microchip logic compiler figure out how to optimize these equations and create the configuration file for the GAL 16V8 chip. Now I'll briefly walk you through how I use the Microchip WinCouple2 compiler to configure and program the I/O expansion board decoder logic into a single GAL 16V8 chip. This is a quick demonstration of the WinCouple2 application, which is beta at the moment and missing some features, but it has enough working features to complete a GAL configuration, including compile, test, and JED file creation. So I took the equations shown in the slide presentation earlier, and I copied them into what will become an input file to WinCouple2. There are four main sections to this input file: a header, an input list, an output list, and an equations list that represents the output functions of input. Next, using those equations, I created simulation data, which is composed of three sections: a header section, the list of inputs and outputs, and the test vectors with values ordered as described in the list of inputs and outputs. This will be used to test my logic description before it's programmed into the gal chip. That section 3 is most like a truth table. So first I'll create a new project. The device family is going to be 16V8B. Package type is 20-pin. And the option, I'm going to use auto. I'm going to let the compiler decide the best optimization routes. Then create a project. And this is just a reminder that there is a limit to the length of the project name, and you don't want to use any spaces. So I'm going to call this 8080 IO-decode and press save. WinCouple2 then creates for me just two workflows that'll result in a working JED file for the gal chip: compilation and simulation. From that workflow, I'll start with the new design file and paste in this input data. New, then move that over here, and then I'm going to copy this information in. File and save. I'll close this. Next, I'll input my simulation data. New, move this over here. Copy all of this in. There we go. File and save. And I'll close it. Next, what I'm going to do is press the simulate button. The simulate button will compile the gal information and then test it. And I should be left with a set of files here that I can use to set up the gal chip. Press simulate. Usually takes a few seconds. There we go. Design compiled and simulated successfully. And this is the JED file I want. This JED file I'll use to program the chip. Now that I've got a simulated design, I'll bring up the programmer. And I've picked a GAL 16V8. I've used the lattice tree in order to select the device. You do need to use the correct device. If I picked an Atmel device, I would get programming errors. But you select, since this is a lattice device, I select lattice. And it can be any one of these as long as it's 16V8. And I'll just press select. And the first thing I want to do is erase the device just in case it already has something on it. So I press erase and then erase. And that succeeded, so I'm done with that. Next, I want to load my JED file. And that's this 8080 iodecode.jed. So I'm going to load that. And then I'm going to program that into the device. You can actually see the fuse map settings further down. Those are all the bits for the fuse map settings. Then I'm going to do a device and program. That's completed. Now I left the lock bit set as default. It's what it does on this application. This prevents somebody from reading out your bitmap, your JED information. You can turn that off simply because it's unlikely that there's any intellectual property here that needs to be protected. It's up to you. So now we're ready to use the device in the system. What I usually do is I'll take these out and I'll put them on a breadboard and I'll just verify using the breadboard that the chip works the way it's supposed to. Now that I've made all the hardware modifications needed and made all the technical decisions needed, it's time to work on building the I/O expansion card. This is the schematic for the card. On the left side are the drivers for the address, data, and control lines from the main board. I always include these for two reasons. They clean up the signals from the main board and they provide some isolation for the main board. There's a lot of wiring these signals have to travel through. Adding drivers will help avoid frustration later with a system that sometimes works and sometimes doesn't. A wiring mistake made on the I/O expansion board will be unlikely to crash the main board. In the center is the GAL chip. This is the address decoder. We also got the bit clock for the second serial port. A little further down to the right, it's a serial port, and below that's the parallel port. Even further to the right are the interfaces for RS-232. Now I'm using TI, Texas Instruments, Max 232 chips for the 232 interface. These chips contain their own charge pump type power supplies for converting 5 volts into the positive and negative 10 volts needed for RS-232. A single MC1489 down here handles a leftover input signal. The dip switch down here, the lower part of the parallel printer lines, is used to adapt the interface to various printers that configure some of the Centronics control lines differently than the IBM standard pinout. I'll be attaching a Tandy DMP100 with an IBM to Centronics cable, and there are 2 control lines from the DMP100 that need to be disconnected to avoid conflict with this 8211 printer port. I used dip trace to draw the schematic. When the schematic is completed and verified, I do the component side layout for the board. It's critical to get this part right because from here, everything gets much harder to change if you make a mistake. I use Visio for this, but any 2D drawing software will work. And this is the bottom side of the board. I lay out the power supply runs using copper tape and solder the tape to the board at regular intervals. Each copper run is terminated with a 10 microfarad electrolytic capacitor. Now each chip is bypassed with a 0.1 microfarad capacitor from 5 volts to ground. This method provides a very stable power grid over which I run all the signal wiring. So this is what the top side of the completed board looks like. Here's our drivers over here. There's the GAL chip, it's the decoder. And this is the expansion bus that plugs into the main board. So over here, everything is, this is the dirty side and this is the clean side, if you will. And here we've got the serial port. This is the serial UART, and this is the 8211 parallel port. And we've got the interface RS-232 interface chips here. And right here is where the back panel plugs into the board. Same thing here. This is where the back panel parallel interface connects to the board. And this is the bottom side. I use the wiring pin method to make all the signal wiring connections. I like this method because it provides an almost PCB-like profile. It's very reliable. Boards I've wired this way 20 years ago are still working today. There's no long pins sticking up from wire wrap sockets or anything like that. But this method is, for some folks, very tedious. For me, it's actually, strangely, relaxing. I'm able to pull the board out, sit in front of it, and start soldering some wires to it. I think I find it as relaxing as some folks find knitting or cross stitching. And this is the expansion board installed on the main board and secured with screws and brass standoffs. All of the wiring is connected to the board. This is the parallel printer wiring. Comes down. There's the DB25. And then the serial port is connected here, runs across. It's connected in the middle. And the console port just extends from underneath this board. It's connected to the main board, and it connects to this top DB9 connector up here. Overall, I think it looks very clean, looks very production-like. And this is the completed computer fully assembled with the printer and null modem cable attached to my main desktop computer. Now that this video's gotten a bit long, I'm going to present CBIOS drivers that I've written for CP/M and demonstrate this computer working with the I/O expansion board in the next video.